Okay, the common ion effect. In this video, I'm going to talk about it just in a qualitative point of view. I'm not going to use any numbers. And then I'm going to do a subsequent video where I show it with numerically. Okay. So the idea here is if you have a salt and you're trying to dissolve it in water, if you try to dissolve that salt in pure water, a certain amount of it will be able to dissolve. If you try to dissolve it in water that already contains one of the ions in the salt, the overall solubility of that salt will be decreased. So let's say, for example, we had a thing of pure water, and we had another thing where we already have some calcium nitrate dissolved in that water. And what we're going to look at is we're going to compare dissolving some calcium hydroxide. Calcium hydroxide has a limited solubility, so not that much of it will dissolve. So in this one that already has calcium nitrate in it, and I'm going to use colors for this to keep these things straight, my calcium I'll make red. There's already some positive ions, I wish I hadn't made that so big, but that's okay, floating around in this solution. And there's also some negative nitrate ions. The negative nitrate ions in this case aren't going to matter all that much because the nitrate itself as an ion is very soluble, so it's not really going to participate in the crystallization process or in the salt coming out of solution, but we should still acknowledge that they're there. And here we have our pure water, and we can see in our pure water that we don't have any dissolved ions at all. So this is our pure water, and this is our water that contains calcium nitrate aqueous. And I didn't put twice as many negatives as I put positives, but they are, and those are 2 pluses, not 1 plus, but it doesn't really matter in terms of seeing what's going on. So here's our common ion. Now we're going to imagine adding a salt of calcium hydroxide to this. So we're going to add some calcium hydroxide, some CaOH2. Now I've already used red for my calcium ions, so I'm just going to put a bunch of calcium ions. This represents our crystal. And for nitrate, I'm going to use green, or not nitrate, hydroxide, I'm going to use green just to keep it separate from the nitrate. So here we can see if we add that crystal into this water, and here we can imagine adding the crystal into this water. Like that. Now, initially, in either situation, an equilibrium must be formed when the forward reaction and the backward reaction rate are equal. So when the ions leaving the salt, when the pluses coming out of the salt, and the rate at which the pluses rejoin the salt becomes equal. So rate ion leaving equals rate ion rejoining. Even in very low solubility salts, this requires some number of ions to leave the crystal and go into the solution in the first place. If there's no crystals in the solution, then there's no crystals available to rejoin, so this rate would be 0. So any salt you put in, no matter how insoluble, a tiny, tiny, tiny part of it is going to start by jumping into the solution. So even in pure water here, we're going to get some calcium and some hydroxide leaving the crystal. And once we get a little bit of it having left the crystal, then it can start to come back to the crystal and rejoin, and these two rates can become equal. The difference is when we have a common ion previously dissolved in the crystal, there's already the pluses available in the solution to start trying to rejoin the crystal in the first place. There are no minuses, so the rate of leaving and the rate of rejoining can't be equal to start, but you really only need to put a very small number of minuses leaving the crystal going into solution before the pluses that are available work with the minuses to rebuild the crystal as fast as it was being depleted. So here maybe we need to get, you know, a 100th of a gram or a 10th of a gram into solution before these two rates can become equal. Where here, because we already have lots and lots of pluses to work with, we really only need to get a couple minuses into solution before this comes back. What that means is these pre-existing pluses will make it so that very little of the salt needs to dissolve before the combined concentration of the pluses and minuses is enough to rebuild the crystal as fast as the crystal is being destroyed and reach equilibrium. So what that means is very little of this salt will dissolve before reaching equilibrium in comparison to how much of the salt would have dissolved in pure water. The existence of that ion has to be common. It has to be something that can build the crystal in the same shape and size that it was when it was placed in. So that's why these two things, to meet the common ion effect, both have to have the same ion in them. But as opposed to needing to build up the concentration of both ions, here we only need to build up the concentration of one ion, and that allows us to have a lot less dissolve. So that's how having a common ion in the solution can limit the solubility of a salt that's put into that liquid in comparison to what the solubility would be in pure water.